Next, let's talk about propagation of error. After watching this video, you should be able to propagate errors associated with a series of measurements, given the appropriate equations, and also state and then apply the common sense rule of significant figures.
So essentially what you have are a couple of measurements here, and you have masses and you're trying to add them together. And each of those masses has an error associated with it. And so the question is, how do you calculate the error associated with the final measurement? So the nomenclature that we're using is E1 and E2 and E3 are all errors associated with individual measurements, and then EF is the final error associated with the calculated All right, so let's talk about random error propagation. When you are doing addition and subtraction, the final error is equal to each of the errors that you're trying to add together. You square them, each of those, and then you add them together, and then you take the square root, and that's your final error. For multiplication and division, it's a little bit more complicated. You use the percent error, so that's the error associated with each measurement divided by the value of the magnitude of the measurement times 100%. And so then you use your percent error, you square each of those values, add them up, and then take the square root. And that is going to cover 99% of all of the error that you'll probably ever have to propagate. There are some oddballs. They're covered in your they're in a table in your textbook, and you can just go ahead and look.
Here you see the
First,
propagation of error table from your book.
Another way to think about significant figures. When you're in the lab, you should always record all possible significant figures. And so, for instance, here is a meniscus of a liquid in some kind of glass tube, and so you can see that the bottom of the meniscus is between 2.1 and 2.2, but you can see that it's not equidistant between 2.1 and 2.2. So you get to actually estimate how close it is between the two different marks. So I estimate that it's 2.18. That the measurement is 2.18, but you might say 2.19, but that is the last digit because I'm uncertain about the last digit. So the rule is that the last digit that you record is the first digit that you are uncertain about.
You already know that there's uncertainty associated with every measurement. When you're talking about something like a ruler, it's important to know that you read one more digit than you're absolutely certain about. So in this instance, if you're reading percent transmittance, you're going to say that it's 58.3. And so you already know that it is between the 58 and the 59, but it's closer to the 58 than the 59, and you can estimate the relative distance between those two digits. So make sure that you record one more digit than you're absolutely certain about. Your a digital balance already does this for you. We just talked about recording one more digit than you're absolutely certain of when you're making measurements. Another important common sense rule is that a measurement can only have one uncertain digit. So what I mean by that is if you have some data that suggests that a penny weighs 13.2305 plus or minus 0.04535 grams, you actually can't have that many digits because there's only one digit allowed in the plus or minus, one significant digit in the error measurement. So if you were to write this properly, you would say that there's 13.23 plus or minus 0.04 grams. Test yourself to be sure that you're able to do these propagation of error measurements by doing the problem below.